It was a calm and cloudless night, but it was all still a blur. A shaking of our universe was just about to occur. It was summertime, 1609, when Galileo used his telescope for the very first time.
We have had some pretty good events lately. We had the Venus transit. We actually we did this out here. We had to do it outside because it was a voting day, and this building was off limits, but we ended up getting 400 people to show up for a transit in the rain. There's no volume on that. There you go. How about that? Is that better? Okay. That's good, Jim. I got it here. Yeah. Anyway, so we had about 85 people during the rainstorm itself, just huddling underneath and watched the web links that we had. And when it was raining, we all got into shelter. We watched the downlinks from the SDO satellite and from Mauna Kea. And afterwards, the sun came out. We had a really, really good event. It was a lot of fun. So then we had Summerfest here last Saturday. Saw about 300 people there. So all in all, in the last 2 weeks, we've seen about 700 people as the club and done a lot. I want to thank everybody that did come out to help with those two events. They were a lot of work, but a lot of fun too, and we got a lot of recognition out of it. So the club has been in one form or another of media or newspaper in town 10 times now in the last month. So that's good. So Al was wanting me to point out that the next meeting is the barbecue. It's the barbecue right here. Starts at 3 o'clock in the afternoon out here on the deck. And it's potluck, so bring something. We'll take care of the brats and bruns and chips, but if you want a side dish or something, bring those along, and we'll have our little picnic out here. We won't be able to view until about midnight anyway, so we won't do any viewing or anything. We'll have a couple of oscilloscopes set up, but that's it for that. So
I'd also interject, this would be a great time to bring along stuff that you want to just chat about. If you have trouble with your telescope or your lunar student how to work the sky program, something like that, this would be a great time to just come and find somebody that knows something about it. Come to list of things you want to chat about.
Remember, it's a party. It's nothing formal like this, so come with a party attitude. So, all right. Well, my name's Zerby. We're here to talk about robots in space. So let's get started. I would say leave these on. I don't know, can we? That's plain right there.
You want these on that?
If we can, can everybody know? See, we can go ahead and turn them off, I guess. Well, I guess we'll skip that slide. We're supposed to start, but there it goes. Now we'll start. Forgive the commentary. My cousin took this video a few years ago. This is actually the Cassini space flight here. This is part 2, Robots in Space's lecture series that Jim and I started last year. We started in 1957, October 4th, 1957, with Sputnik. And we worked our way up to the ending last year was what we're going to talk about this year. The future of what we're doing in our solar system as far as manned spaceflight. Again, my name is Zerby. Jim Bonser's going to talk to you here in a little while about some of the not so well right, yeah, the missions that didn't turn out quite as well as we had hoped. So we're going to talk about 4 craft tonight for the most part. The James Webb Space Telescope. This is the replacement for the Hubble Space Telescope. Replacement is kind of a misnomer. We'll get into that in a little bit, but it is the craft that's slated to replace our balloon Hubble. The New Horizons spacecraft. New Horizons is a mission to Pluto. Robonaut. He's a bipedal humanoid astronaut that is in space right now working for us.
Why did you have a break?
I think that's an impact wrench, but I like ray gun. We'll go with ray gun. And of course the rovers, the twin rovers on Mars, Spirit and Opportunity, they're everybody's favorite, the little Energizer buttons, if you will. We'll start with the James Webb Space Telescope. This craft is enormous. There's never been anything built for space as big as the James Webb Space Telescope. It's slated to launch in 2018. It's a little behind times. It's supposed to launch next year. It weighs 14,000 pounds, which sounds like a lot, but the Hubble weighs 24,500 pounds. So this thing is about 4 times the size of Hubble, but it weighs 10,000 pounds less. So you see the advance in technology over the last 25 years, at how much lighter we're able to build spacecraft and how much more advanced we can build. It's a 5-year mission, and the mission is to view the edge of the universe, view back to the Big Bang. It's a 5-year mission, but they're expecting 10 years or better out of it, just as Hubble was a 5-year mission, and we've got 20-something years out of it. So it was named after the great NASA administrator James Webb. James E. Webb was the second NASA administrator. That's him right there, fine-looking gentleman. He was largely responsible for the Apollo program. James Webb oversaw more launches than any administrator to date. It's currently cost us $8.7 billion, which is $8.2 billion over budget. They started planning for James Webb in 1994. You know, they put the Hubble up there, and the first pictures that came back were awful. And immediately they started planning the replacement craft. Well, in the meantime, we fixed the Hubble with the Coast Guard unit and several other servicing missions. But they started designing this as originally only supposed to be a $500 million project. NASA has capped the budget on this project 11 times. Apparently that doesn't mean much, but they have. It's been canceled 3 times, and they keep resurrecting this thing. So it's going to have its own orbit around the sun. It's going to set out at the Lagrange 2 point. It will not orbit around the Earth. It will orbit around the sun with the Earth. Here's an illustration of the differences here. You see Hubble, its orbits at 353 miles. So it's in Earth's atmosphere. 930,000 miles is where James Webb is going to orbit. We're 93 million miles from the sun. It's going to orbit at 930,000 miles. It's roughly 1% of the distance. It's a gravitational hole. The Lagrange points are gravitational holes in which the spacecraft we can put something there, and if we don't have to worry about trajectory, we don't have to worry about thrusters or anything, it will just stay there. Now, it won't just be a rock out of the L2 point. It will actually orbit. Its orbit is a 500,000-mile orbit, so it's twice the distance between the Earth and the Moon, but it's a 500,000-mile orbit around the L2 point right here. You can kind of see a difference here. There's Hubble squished up right close to the Earth, the Moon. James Webb is way out here. There's several L2 points, or L points, excuse me. There's 5 Lagrange. You have the L2, L1. These are 1% closer or further away from the sun than the Earth. And then you have one that's out here at 60 degrees, another one at 60 degrees, and one polar opposite from the sun that we are. Believe it or not, you put something out at L3, and it will orbit around the sun in time with the Earth because of the gravitational pulls. So. Moving on. Here's a good demonstration of the difference here. This is the Webb mirror. It is an 18-segmented gold-plated beryllium mirror. It's, again, enormous. There's no other word to describe the Webb than enormous. And this is me. I'm 6 feet tall. This is the Hubble mirror at 8 feet. And this is the Webb mirror. I need a volunteer. Can I get a volunteer out here real quick? Anyway, okay, come here. We have a tape measure, simple tape measure. So let's take that. And that's how big the Hubble mirror is. Why don't you go over there? Just take the tape measure and keep going. Yeah, keep going. There you go, that's good. This is how big the Webb mirror is. It's huge. Now think about it. Look how big this is. We don't have any spacecraft this big. We don't have any rockets big enough to be able to put this in. So we have to fold up the mirror. Thank you, that's all. I was actually going to have them help me with the overall size of the craft, but in a minute you'll see why that wasn't practical. Each one of these segments is about a meter, 6.5 meters across, which works out to, I think, about 22 feet, or excuse me, 24.3 feet is how far across it is, versus 24 or 2.4 meters, which is about 8 feet for the Hubble Mirror. There's roughly 7 times the collecting surface in the James Webb Telescope mirror than there is in the Hubble Mirror. This is one of the mirrors right here. This is actually the very first mirror that they finished and polished. It is gold-plated, 24-karat gold-plated. The back side of it is carved out like a web, oddly enough, for the James Webb Telescope. It's a hollow structure, so it just has these crisscrossing lines of solid metal in it, but most of it is air pockets. I have a really great video that we don't have time for today, but I'll put up on the website for you. That is how they start at the beryllium mine and go all the way to the stage. So that's really neat. I've got some handouts here. Got to start. We'll get them started around. For all 4 spacecraft that we talk about today, there's a link to the NASA page on it. Some more information that you'll be able to go there if you want some more information on that particular spacecraft. So let's talk about mirrors for a second here. In '93, when they put the Hubble up, and we had these awful pictures come back, and there was this problem, to say the least. The problem was the mirror was ground perfectly. There had never been a mirror ground so perfectly. They ground it the wrong shape. It was ground perfectly. How perfect is perfectly? If you were to expand the Hubble mirror up to the size of the United States, the largest deviation in that mirror would be 6 inches. This mirror is roughly 100,000 times more precise than the Hubble mirror. We're now in an age when nanotechnology and things of that nature allow us to be able to create much finer pieces of engineering. If you were to expand this mirror up to the size of the United States, the deviation would be less than 1/10 of a millimeter. And there's 18 of them. Here's the first 6. These are called flight-ready mirrors. These are the first 6 mirrors that are going to go into the spacecraft. This chamber right back here is the cryogenics chamber in Houston. They put them in there. They cool it down to 3 degrees above zero, absolute zero. So 370 degrees below 0 Celsius. And they do the cryogenic testing. The reason they use beryllium is because it has really great expansion qualities. In other words, it doesn't. You can heat it up to 300 or 400 degrees. You can shrink it down to 300 or 400 degrees, or cool it down to 300 or 400 degrees below 0, and it doesn't expand. So we'll be able to put this stuff in space, and how it sits on the ground will be exactly how it sits in space. It's extremely stable material. It's also poisonous, so the people working on it had to work on it very special gear and things of that nature. So we talked about how big this spacecraft is, and I can't reiterate how big it is. If it wasn't raining today, I was actually going to have it drawn in the parking lot so you get an idea as you walk in how big it is. It's 76 feet long. How long is 76 feet? Well, I tried to measure from here to the window in the kitchen, and that's only 69 feet. So I was going to do the same thing with the tape measure, have somebody run out to 76 feet, but the building's not big enough. It is 47 feet across. Side ride bus is 43 feet. You can put a side ride bus across this thing and have 4 feet extra. Anybody play tennis? It's larger than a tennis court. And the Hubble was one of the biggest spacecraft ever built up to this point, but it just doesn't compare to what. That's a proper scale comparison. That's 171 people standing in front of the model of the James Webb Space Telescope at Goddard Space Flight Center in Maryland. This is the 171-person crew that's designing and building the James Webb Telescope. They could fit on that sun shield several times over. We have this giant spacecraft. How do we get it in a rocket? Well, we wad it up in a big ball. How do we get it out of the rocket? Very carefully, is what I was told. This is how we get it out of the rocket. The nose cone separates, the fairings come off, the cowlings dissipate, and it starts to unfold. First thing to unfold is the solar panel, and the antenna. This little guy down here is the high gain antenna. Angry. I think we have to wait for it. Well, anyway, we can talk about this while it's doing its thing. These are the solar shields. The solar shields fold out and then unravel. And then the mirror itself, see if it'll let me start it over. Well, we're just going to have to ignore that again. And it won't. There we go. We'll see if it does any better. It's not going to let me do anything else until we see it. So that's the solar panel there. Then the IGN antenna drops down. And that sends information back to Earth saying we're in position. Did everybody get one of the handouts? Okay, that. So everything unfolds and locks into place. Then the whole telescope boom assembly, you can see the model up there that I built. The main boom assembly motors up, and then the sun shield itself starts to unfurl. If I could have sped up this animation a little bit. Yeah. The video. Well, this is actually sped up quite a bit. They figure the full time is about 3 to 4 hours. So there's 5 of these sun shields. They're a silver-plated mylar. Each of these the sun shields drops the ambient working temperature down 12 degrees. So 5 shields, 12 degrees, 60 degrees. This telescope operates at 7 Kelvin. 7 degrees above absolute zero. For those of you that are unfamiliar with absolute zero, it's the temperature in which all motion in the universe stops. Molecules don't wiggle anymore at zero. So this here is a very interesting thing that I've just learned about. This is the momentum flac is what it's called. And we keep talking about how big the telescope is. It's so big that the solar wind will actually move it out of position. So particles coming from the sun, hitting this, there's enough of them, it will actually rotate it off of its target star. And it's broken again, that's all right. We'll move over to something else. It's a collaboration between the 3 major space agencies, the Canadian Space Agency, which I didn't know something existed, the European Space Agency, and NASA. And it's funny, if you look at the budgetary work here, NASA has put in $8.3 billion. The European Space Agency has put in $330 million, and the Canadian Space Agency, $39 million. Now, in that grand scheme of things, I wouldn't even think you'd get your name on the paperwork for $39 million, but they actually built one of the instruments. NASA got it at Space Flight Center, the picture I showed you there, of all the people standing in front of it, the ones that are controlling the development of it. It is a product of Rover. And that big model was part of the contract. When they got the contract from NASA, they had to build that model. And anybody that requests that is put on a list. And they go through, and organizations, they've taken it to elementary schools, Northrop Grumman has to pay to take that to anybody that has to borrow it. So I'm going to be calling them next week and see if we can get it here, but we'll probably be at the top of the list, don't you think? The Space Telescope Science Institute, that is the organization, of all things, in Johns Hopkins Hospital, which is where the Hubble Space Telescope is controlled. It's at Johns Hopkins Hospital. The Space Telescope Science Institute will also run the James Webb. So the James Webb will also be run out of Johns Hopkins Hospital. It's an odd place, you'd think, for this, but that's where the funding came from. So the main spacecraft instrumentation, there's 4 instruments. There's many instruments, but there's 4 main instrument groups. The NICAM, if any of you are creative at all, you can probably figure out that that stands for the Near Infrared Camera System. It was designed by the University of Arizona, who also has the largest mirror lab in the world, and was built by Lockheed Martin. Now the next one is a real stretch. NIRSPEC, which stands for Near Infrared Spectrograph. Again, not a lot of creativity with the naming of these systems. It was built by the European Space Agency. MIRI is the Mid-Infrared Instrumentation System. It was built by JPL, which is in California. That's Jet Propulsion Laboratory. And then we have this guy. I'm not even going to try to make it a word. FGS-NIRISS stands for Fine Guidance Sensor Near Infrared Imager and Slitless Spectrograph. 9 words. Abbreviations are supposed to be really short. This is the $39 million unit that was built by the Canadian Space Agency that got their name on the spacecraft. The 4 main science missions. I told you earlier, we're going to look back to the beginning of time. The end of the Dark Ages is what it's called, and I've got a graph to show you that here in just a minute. After the Big Bang, everything cooled down, and as things started to become matter out of energy, the reionization of energy into matter, first life in the universe, if you will. The assembly of galaxies. We'll be able to look so far back, we will literally see fields of stars beginning to gravitationally swirl in around the mass of those stars and create the very first galaxies in existence. The birth of stars in protoplanetary systems, the same thing. A little older, if you will, than galaxies themselves. We'll see stars born, and we'll see the planets themselves start to accrete from the disk of matter around those stars. This one's fun. Planetary systems. Planetary systems are extrasolar planetary systems. Other stars, planets around those stars. The origin of life. Right now, everybody's familiar with Kepler. We're staring at these stars out there, we're watching them blink, we watch them wobble, we read the redshift, and we know they have planets. Well, we know they have giant planets. Most of these planets are 12, 15 times Jupiter's mass. They're enormous. It only takes 1,000 Jupiters to make a star our size. So a 12 Jupiter mass planet is an enormous planet. But what Webb will be able to do, not only will we be able to detect the wobble of these stars, we'll be able to see the planets around the stars. And we'll be able to see Earth-sized planets around the stars. Here's the breakdown of the different spacecraft. We have a lot of space of telescope observatories up there right now. This is Swift. Swift uses gamma rays. Back to the very, very early days, it looks at black holes, quasars, cosmic relation of gamma rays, and things of that nature. RXTE, I don't know why they didn't put Chandra, but that's the Chandra X-ray telescope. And it looks for X-rays. Again, black holes, X-ray radiation, things of that nature. And then the Hubble Space Telescope, our beloved Hubble. Let me tell you, it's going to be a sad day when they crash that thing into the ocean. I'm not ready for that. It's centered right in the middle of the green band of visible light. You can see mostly ultraviolet light outside of visible light, and a tiny little bit of infrared. In fact, it's got a device on there. One of the science packages is called the NICMOS, which is the near-infrared CMOS package. That's the digital camera that takes pictures in very, very, very near infrared. So Hubble's pictures all come in visible light, which is what we can see. James Webb's will not. Now NASA will be able to take that data and make the kind of pictures that we're so used to from Hubble. You know, everybody is just addicted to those amazing pictures that Hubble brings back. The data that James Webb will accumulate is a completely different set of data. It is not visible light. It's heat. It's infrared. So it will do near and it will do mid. It will be able to see into the orange bands, which are far visible light. But never again will we have a telescope in space that will be pure visible light. So all the images that we'll see from now on will be computer generated from the data that we have achieved in the infrared band.
Look.
And then WMAP, which stands for the Williamson Microwave Anisotropy Probe. It looked back to the microwave radiation after the cosmic background radiation, which was microwave. So that's as far back as we can see right now, is the WMAP probe. We can see back to that cosmic timeline where we were able, microwaves, there's across the board, space is about 3 degrees difference. And the microwave radiation, depending on what frequency it comes in, actually tells us the temperature of those areas of space. And we have some balls that NASA has sent us, which are beach balls that are actually a map of the entire universe. After the visible, the light horizon anyway. And it's WMAP, it's the microwave map. And then of course radio waves, which this is the BLA, which is the very large array of telescopes out in the desert. So here's what we're talking about. HST, Hubble Space Telescope, the goods package, and the Chandra X-ray telescope can see back to about here. Visible light that we get from Hubble is right in this area. This is what we can see with our telescopes here. The C14 out there, we can see no further past this right here. And Hubble can see here. James Webb, we're hoping to cross this line right there. So Hubble can see back to about 300,000 years after the Big Bang. Webb is hoping to get within seconds of it. This is the Webb cam from the James Webb Space Telescope Assembly Room. There, on that page that I gave you, there's a link to the James Webb. You go there, and down at the bottom, you can log into the webcam. And there's 2 of them now, since this slide was made. And you can watch them actually build parts for it. And every once in a while, you get lucky, they'll roll out a big blob of gold. You know it's a mirror. It's really special to get to see a mirror. And there's actually, you see these little domes here? Those domes hold the mirrors. So there's mirrors there, they're just under half-inch stainless steel. Let's see what's next. Let's see if it plays. That robot you saw there at the end was Robonaut 1, and he was waving goodbye to his brother, Robonaut 2, that left on STS-133 shuttle flight to the ISS. Now, obviously, this is a little old because last July was the last shuttle flight, but this was the flight that took Robonaut into space. It took the first humanoid robot into space. Let's think about that a second. It looks like me. It looks like you. Got 10 fingers, 10 toes. He does have more joints in us, but he can do everything like we can do. The reason for that is as we program robots and build robots, we want them to be able to do the things like we know how to do them. So he has 10 fingers, 10 toes. Although you can change him from the waist down to a lot of different configuration. He moves fast. It's 330 pounds, so he's had a few more cheeseburgers than I have. He's built out of a titanium aluminum alloy. Each arm can hold 40 pounds. Now, it doesn't sound like a lot, but I challenge any of you in here to take 40 pounds and hold it like this for an hour. I wouldn't be able to hold 20 pounds like that for an hour. Probably not 10. He can hold 40 pounds forever. Like that. 350 sensors. He has a sensor in every finger, in every joint. He has a sensor in every muscle. He has muscles. They're electromechanical muscles, but he has muscles. They basically copy human anatomy. Don't know or not. He has a lot of processors, 38 processors actually. That computer that we're running this off of right now, it's a quad core, it has 4 processors. He has 38. He has 350 sensors. It takes a lot of processors to chew through that data. This is the Centaur unit that the Robonaut. I told you can change it from the waist down. The one on the space station now has thrusters. Doesn't need feet. He can float around. This is a Rover type. You can have them then hold to a crane. There's lots of different configurations. There's 4 of them right now. There's 2 Rovers and 1 with feet. It's bipedal walking robot. You let it go, you go over down the stairs, run to Burger King, whatever you want. He walks like we do. The other one is the one with the thrusters. It's the original Robonaut 2, who's on the space station. And they're great for EVAs. The nice thing about the robots is you need to send them out to repair something. Say there's a hole, a meteorite that hits the International Space Station. Tiny one, obviously, a big one to take it out. It takes hours to get a robot, or to get an astronaut into a suit, get him outside. Hours to get him into that suit. 3 or 4 hours sometimes. By then, it could veer it off course and crash it into the ocean. Robonaut can go outside like that, sitting through the airlock and having patched the hole. It's a big thing with BPAs. There's a lot of things Robonaut can't do, because you still want the human touch and the human mind to be able to work around problems that arise when you're doing something. But for stuff like that, you cannot be controlled. He moves at 2 meters a second. You saw in that video he was moving around, so like, yeah, how far is 2 meters? Well, it's about 8 feet. Stop. That fast. For a robot, that's fast. A lot of people talk about how NASA's a waste of money. Never get anything out of NASA. I'm a robotics student. That's what I'm going to do. I'm going to try to build spacecraft and robots that go out of our solar planet. And 300 advanced technologies have been gained from the research on this robot. It was originally a DARPA robot, which is the defense research program for the Army. And 300 advanced technologies. Before the robot, we had Osimo, we had a robot that could barely walk. He can walk 2 meters a second. Well, all these technologies have come out from this one thing. Now this is one program, one robot. Think of Viking and Voyager and the space shuttle and the moon reconnaissance, all of the technologies that we have today, cell phones, all the technologies we have today gleaned from the space programs. Like I said, he has sensors in every member, in every finger, in his muscles. And he was a consortium built between NASA and General Motors, so technically it's a Chevy. Now, here's where things get a little interesting. I was doing this research for this, and I know a lot about Robonaut, something I follow very closely. In fact, I follow him on Twitter, and I follow him on Facebook, and you guys can too. He has his own Facebook. It's not somebody on the ground. He has an interaction program that's programmed into him to be able to talk to people on Facebook. So it is the robot, you were talking to the robot. He can be flying around the space station and just take a picture with his eyes and put it on Facebook and say, hey, look what I'm doing. And it's him. So I follow him very closely. But one of the things I didn't realize is the designations. And we'll get into that. This is Robonaut 2, like I said, so they call him R2. Right? Makes sense. He will be confined to the Destiny Laboratory of the International Space Station for the repairs and the research work that they're doing in that particular module. Eventually, he will get upgrades and will be allowed to fly over the entire International Space Station. But for now, the flight patterns and the flight tests are done just in the Destiny module. He is a robot that's still created by man, and there might be something that happens. So if something does happen, they can shut off one module, and they don't have to worry about anything breaking in the rest of the International Space Station. But for now, he's stuck there. The next designation, the robot will be called Robonaut 2 Descendant 1. Anybody see where we're going with this? So Robonaut 2 Descendant 1, he will be the robot that lives forever outside the International Space Station. We were talking earlier about a meteor strike. He'd never have to go through the airlock. He just flies over there and passes. So I got to thinking when I was looking at this, and you all know what I'm thinking right now, but if the third generation is R2D1, the fourth generation is going to be going to Mars. They'll be the rovers, the Centaur units that are going to Mars. And I really, really wonder if that will be Robonaut 2 Descendant 2. But I have to ask myself, is that copyrighted? 5, 4. So we're moving on to the next spacecraft.
2. We have a mission and liftoff of NASA's New Horizons spacecraft of a decade voyage to visit Pluto and then beyond. In just 15 seconds, everything continues to look good as the Atlas V vehicle flies away from Florida's coast. T plus 35 seconds. T plus 4.
New Horizons. We're going to Pluto, folks. I don't know about you, but I'm very excited. July of 2015, it will arrive at Pluto, and once y'all meet me back here, we'll watch it live. How about that? New Horizons is part of the New Frontiers program. Now, what's a program? Apollo was a program. Mercury was a program. Gemini was a program. Viking was a program. New Horizons is part of the New Frontiers program. The New Frontiers program is like, we're going out to these planets, and we're going to take another look at the planets that Mariner, Viking, Voyager looked at 40 years ago. The first one is Jupiter, Venus. We're going to look at Pluto, obviously. There's one that's slated to go to asteroids. Two of them will launch. New Horizons launched in 2006. It's a long way to Pluto, folks. It is the fastest moving spacecraft, second only to Voyager. The difference in speed between it and Voyager is about 400 feet a second. It's moving at 16.7 kilometers a second. So that's here into Beta, that fast. And it does that forever. Juno, which was a spacecraft launched last August, not too long from the over here, is headed to Jupiter. We're going to have another spacecraft at Jupiter studying Jupiter. Here's another one of those crazy abbreviations. We're not even going to go there. But Origin, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. That's a mouthful. Security Regolith Explorer. That boils down to deadly asteroids. We're going to send that out to study asteroids, meteors, comets that could possibly hit the Earth. So that's what REX, we'll just call it REX, is for. Or Pluto. You know, New Horizons is a mission to Pluto. It's a mission to a planet, but Pluto's not a planet. How does that work? New Horizons launched in 2006, and in 2006, Pluto was still a planet. So, it's due to arrive, like I said, July 14th, 2015. I'm planning an event for that. Let me tell you, I am extremely excited. Now let's think here of the Voyager missions. The images we got back from the gas giants from Voyager blew mankind's mind about what was out there. We literally changed everybody's concept of what there was as the gas giants. Like I said, New Horizons was launched, Pluto was still a planet, and since its launch, we've discovered that it doesn't have one, but 4 moons. At least 4 moons. Now let's look at something here. Charon was the first moon. Nix and Hydra. N and H. New Horizons. It's not a coincidence. Nix and Hydra were the two mythological names picked for those moons to commemorate the New Horizons mission. 5 Tombaugh, his ashes are on the spacecraft. Discoverer of Pluto. Announced it was actually good. I don't know. I'll leave that up to you. I'll let you do it. And you know, I called and I talked to my buddies at JPL, and I asked them, "You have a planetary mission going through a rock. It's not a planet." And I was corrected because they said Pluto is a planet. There's no question about it. In the New Horizons team, Pluto is a planet. So, and I agree. I will not back down on that one.
Heaven, it's a planet with an adjective. It's a planet.
It's predicted to have a ring system. That's something that they've been talking about for 20 years now. We hope it has a ring system because that makes it that much more interesting. But this is an artist's interpretation. I wish they wouldn't do that. This is the clearest picture we've ever gotten of Pluto, and these are both from the Hubble Space Telescope. So the artist took this data and made this, and that's the best image with an artist's help that we have of the planet. This is the best we have, and think of the images we got back from Viking. Now think of the fact that we're 40 years more advanced in our imaging technology. It's going to be an epic day when we get first light from Pluto. It has seen Pluto, it sent pictures back, but it's still just a tiny little dot. Well,
8, 7, 6, 5, 4, 3, 2, communication, and liftoff. The Delta II rocket with Mars exploration program.
it wins. amazing all the things that you have to do. You know, the other day, Jim and I were working on this lecture, and he says, you know, everything NASA does is Rube Goldberg. Everything has to go right. You've got this falling into here and pouring water on a fire, and it moves this, and it does this, and then it shoots this off, and we get a spacecraft on another planet. And you think this is crazy. Wait till you see how we're going to land Curiosity. Mars. One of the craziest designs NASA has ever had, as far as I'm concerned. Let's take this $800 million piece of equipment and bounce it off the surface of another planet. Let's see what we can do. I edited this down originally. I put in the number of bounces that were in the official record, but it was 37, and that was way, way too long to watch a big little bounce. It bounced over a mile away. So the Mars rovers are officially titled the Mars Exploration Rovers. We all know them obviously as Spirit and Opportunity. It's an action picture taken by one of the twins. That's Spirit, if I remember correctly. Their official titles are NER, A, and B, but that's not very much fun, so we call them Spirit and Opportunity. Spirit is A. They're robotic planetary geologists. That's what they are. They go out and they look at rocks. And they've been emulated. There's this cute cartoon called Planet 51, and if you ever see it, they've got a rover on there that acts like a dog. He's a robot geologist. He goes nuts for collecting rocks, and it's really cute, but it's after these guys. So, their mission was to study rocks and try to find water. That's the short and sweet of it. They were to study rocks, mineralogy, the formation of those rocks, the intercrystalline structure of those rocks. Total cost of the mission is $820 million. We look at that compared to today's mission prices. The Webb is at $8.7 billion. It's roughly 10 times as much. It's had 6 mission extensions. Originally, they were only supposed to be there 90 days. Only 90 days. And 6 mission extensions have brought it up to $144 extra million. They were launched in 2003, landed in 2004. We're going to talk about Spirit here. Landed at 4:35 ground UTC on January 4th. About 80 days into it. There's a lot of dust on Mars. A lot of dust on Mars. Ultra fine, they say smoke-sided particle dust. And it built up over the solar panels to the point where it was down to something like 85 watt hours, and it's supposed to run at 435 watt hours. So it just was dying. And they had given up. They were writing final reports and stuff like that. Remember, they were only supposed to last 90 days. They got 80 days out of it. They thought, hey, we're happy. Day 91, they got a signal that says, hey, I'm still here. Don't tell me how good. Wind had come through. It's called the cleansing event. It didn't have a title until this had happened. NASA had to give it an official title. Wind came through, and it blew the dust off the rovers, and they woke up. And this happened to both of them on the same days. They weren't that far from each other. And they woke up. They resurrected. So it was only supposed to move 600 meters. That's 0.4 miles. Now, if you've ever been out here and done our tour of the solar system, the short path for the tour of the solar system out here around this is a half a mile. So this trail right out the door here is longer than the rovers were originally supposed to move. Now, mind you, this is just Spirit. but it lost 7,730 meters for decay. That was a typo. It's only supposed to move 600 meters and move more than 10 times that. 4.8 miles. On May 1st, it got stuck. Boy, did it get stuck. It buried. High-centered on a rock and a dirt pile that was really soft and sunk. And they tried for 9 months to get it out of the hole, and they finally said, you know what? We can use this rover as a stationary platform, science platform. We can test winds, we can do things that we couldn't do if it was moving. So they wrote new missions for it. And they were able to keep using it for quite a while. Unfortunately, 2010, in March, it stopped talking. Never to be regained again. They tried again another 9 months to build the communication back, to get it back, and they never did. And I believe it was July, they did a press conference. And they had a wake for him. they had a little funeral. And actually, the rovers have got the Congressional Medal of Honor now. Which I find, I love the rovers. I mean, they're supposed to go for 90 days, and, you know, his brother here, Opportunity, landed just 3 weeks later. The other mission, Bridgeport's January 25th. They were also launch students in Florida, obviously. Planned mission of 90 days, again. Except, it's still running today. It's still doing science. It's now gone from what was supposed to be 2 craters, it's seen 14 craters. 34.5 times the mission length, and there's really no end in sight at this point. It's currently winter on Mars, so it's kind of huddled down. It's got one solar panel over its head to protect itself in the winter, but it's still taking data. It's still doing wind measurements and things of that nature. It's currently kind of in a standby mode to protect itself, but winter it's spring actually at this point, and so in the next couple months we'll start hearing about more stuff from it. It was only supposed to move 500 meters. Now remember, brother, Spirit, is supposed to be 600 meters, moved 7,700 meters. It was only supposed to be 500. Spirit's dead. Opportunity's still alive. 34,365.04 meters. So that little rover is about to Colo Island at this point. Odometry is actually a new word that NASA made up. Microsoft does not like it when you use it, but odometry is the distance traveled of a spacecraft. So 34,000 meters, that's 34 kilometers. 21.5 miles. Actually, that's quite a bit further than Colo. Now think about it. 6 miles further than Colo. It's currently at Greeley Haven. It's kind of a plateau area where there's some rocks, and it's tucked in by these rocks to protect it from the winter. But that's what's saying right now. Greeley Haven was named after a geologist. 2007, Spirit discovered water. It was water molecules. But it found water on the surface. Frozen, but water molecules. July 31st, 2008, the Phoenix lander proved it. It directly sampled water out of the soil. It's a neat story about Phoenix that I absolutely love. You know, it had been there for a while, and they hadn't found anything. They're doing all these different science tests and stuff, and running these different experiments, and the team was starting to be bewildered. They were starting to fight amongst themselves a little bit. And everybody was arguing, oh, we're going to find it, or we're going to find this, we're going to find it in this form, this type. Nobody knew. And as they're sitting there, the next image comes up from the Phoenix lander. And I told you about this little operation that they do, where they kind of like a bird, they tuck their head in underneath their solar panel. When they can do that, they can see the lake from lander. And lander sent back a picture of water running down the legs of the lander. The morning frost had started to melt, and it was running down, liquid water running down the legs of the lander. And here are all these scientists that were just in the middle of an argument about it, and they look up and there it is. They were looking in the wrong place. Okay, so the Mars Science Laboratory, you know, we talked about this guy we've got to talk about. We're not going to talk about him much. Today, anyway. He lands on Mars in 50 days, guys. In August. So in August, we'll have another spacecraft on Mars. I for one, think we should plan an event for it. Let's get everybody together and watch it land. 50 days, 4 hours. And that's from right now. Actually, I did the math. 50 days, 4 hours. No, this is current time. This is U.S. time. Oh, right. Jim says, remember we're talking about Mars. Jim is going to tell you about why Mars is the forbidden planet here in just a minute. So, but it's going to land on August 6th, 2002. What? 2012. Yeah, I read it wrong. So let's take a break real quick. Jim's going to talk here in a minute. We've been sitting here for quite a while, I know. If you came in late, we've got refreshments up there, popcorn and lemonade. We also have some raffle tickets. We're going to do a raffle after Jim's done. So make sure you guys got some tickets, and we'll come back in 5 minutes or so. Okay?
Yeah.